It's a pleasure to have Dr. Peter Petreczky for today's colloquium. And Peter also visited us last time, so some of you were not interacted with him. So he is now a group leader and distinguished scientist at the National Laboratory. He has been there since 2002, and he is one of the pioneers in our field in terms of charmony, heavy quark, form states in finite temperature. And now he's also working in many aspects of EIC, physics related to electron and collider particle distribution functions. And he has worked on a large area in lattice QCD, and he will give us an overview of his view on strongly interacting matter at finite temperatures using lattice QCD.
Thank you very much for this nice introduction. So I'm going to tell you how we explore the strongly interacting matter at high temperature using lattice QCD, and question we are trying to answer to what can be learned about from quantum chromodynamics about the property of nuclear matter at very high temperature when we solve quantum chromodynamics on supercomputers using kind of the formulation that is known as lattice QCD, where we put lattice quantum chromodynamics in a discretized space-time. And more specifically, I will talk about the chiral transition and the equational state, fluctuation of the conserved charges, and the deconfinement, so how the fluctuation of conserved charges are related to deconfinement. And finally, I will discuss the transport of heavy quarks, namely the heavy quark diffusion coefficient, how it's being calculated on the lattice. So just a brief introduction. So what is quantum chromodynamics? They are more than a theory of strong interaction, and it describes the structure interaction of hadrons. So it's a non-abelian gauge theory coupled to fermions, in this case quarks, and it has a very simple Lagrangian, kind of amazingly simple. So it's reminiscent of the Lagrangian of QED, quantum electrodynamics, with except that now the fermions carry additional index color denoted by alpha. And of course, that has a lot of consequences because if you have these three colors, so it's therefore you have an SU3 gauge theory, and the gauge invariance, of course, dictates what the stress tensor of the gauge field should be, and it's like the stress tensor in Maxwellian gauge theory, but it has this nonlinear term, which means that gluons and like photons self-interact, and this self-interaction, so this very term, which kind of changes the theory completely, so it has asymptotic freedom at very short distances or very large energy scales, as a strong coupling constant alpha s goes to zero as distances, approach distances become smaller, the energy scales become smaller. On the other hand, when we go to large distances, this coupling constant becomes large, so the interaction becomes stronger, in so strong that in fact quarks and gluons can never become a free particle. They're always confined inside hadrons. So what we see in nature are not quarks and gluons, they are kind of objects which neutral with respect to this new color charge. So they're either objects composed of quark and anti-quark, which we call mesons, or three quark systems, which we call baryons. And of course, for discoveries of this asymptotic freedom, those Povitz and Luch of the past 2004. So the rough with a scale where the interaction changes from weak to strong is given by this number 200 MeV. So that's basically 5 times smaller than the proton mass, roughly, and that's a scale where you transition from this weakly coupled feature of quantum chromodynamics to strongly coupled. Now, in nature, we have different types of quarks, so the different flavors of quarks. So the light quarks, which kind of precise the matter, nuclear matter, and nuclear is up and down. There is this kind of intermediate strange quark. It's still relatively light, so compared to this typical scale. And there are, of course, heavy quarks that conclude in the charm bottom and the top, which is the case very quickly, which have masses which are much larger than this characteristic scale on the QCD. And this, of course, also makes them special when we go the strongly interacting matter at high temperature. So here, just to put things in perspective, so here is a strong coupling constant as function of the energy scale. So just to compare, it's actually pretty large. So even when you're talking about coupling constant being small, it's still kind of 10 times larger than the coupling constant in quantum electrodynamics, and then of course you go to low energy scale, kind of rises and goes to pretty large values. So that's kind of the strong coupling constant is below extracted from different experiments. And that, of course, explains the proton mass puzzle. So if you try to put 3 quarks, of course, you won't get this mass of a proton, which is about 1 GeV. So that would mean that instead of 3 quarks, you need 300 quarks. So actually, the way you make the mass of the proton is that this quark interacts strongly, and by equivalence principle, of course, the strong interaction energy between quarks and is responsible for mass of the proton. So now there is another other aspects of QCD which is also important, which are related to global symmetries of QCD in general and QCD also in finite temperature. So there's a chiral symmetry, which comes from the fact that the up and down quark masses are much smaller than on the QCD. To the first approximation, you could neglect the quark masses in a range of up and down quark, right, because they're so small. And in that case, the QCD has this approximate symmetry, which is called the chiral symmetry, which is you could do a rotation, this chiral rotation, non-flavored chiral rotation, where you replace the quark field by the rotated fields with gamma phi matrix and this flavor matrix A. And of course, if there is a quark mass is 0, that would be an exact symmetry. So that means, of course, if you write in chiral basis, so you kind of separate the left and right-handed component of the fermion spinors, then it means that the symmetry implies that the left and right-handed component would be rotated independently, and the branching is still symmetric. But the ground state is not, because if you calculate the chiral condensate side by side, of course, that mixes the left and right. And if this chiral condensate is non-zero, and it happens to be in QCD, then it means that this chiral symmetry is broken. So it's broken spontaneously, so that we have a Nambu-Galton realization of the chiral symmetry. And that, of course, has kind of important consequences. So in particular, hadrons with opposite parity have very different masses. And of course, so this chiral symmetry responsible for the fact that, in fact, the interaction between hadrons themselves are weak at very low energies. So while we talk about low energies, of course, being kind of interacting very strongly, hadrons at low energy actually interact weakly. There is kind of a similar symmetry, which is also chiral rotation of fermion fields, but in this case is non-flavored. But this symmetry, which is also called the axial UA1, is broken by quantum effect, so it's not really actually symmetry of QCD. There, of course, discussion whether this symmetry could be effectively restored. This breaking effectively becomes very small when you go to very high temperature, but I won't discuss that. Kind of an interesting topic by itself. It's related to topology in QCD. And finally, there is a center symmetry Z3, which is invariance under the global transformation of the gauge fields that typically finite temperature, as I will show, the gauge fields are periodic, but you could imply gauge transformation which preserves this periodicity up to this phase factor, which is the center of the SU3 gauge group. And in zero temperatures, this is a symmetry of QCD, but finite temperature, the symmetry is broken, which is kind of manifest the fact that this Wilson line, the trace Wilson line, because the product becomes non-zero at high temperature. But again, I don't want to go into that much, as to mention that there is also this symmetry. Now, how we think about QCD at high temperature. So, of course, as I said, we have hadron gas, and because hadrons interact kind of weakly when the temperature is low, so the energy is low, that's really, you can talk here about the gas. So basically you put to the first approximation, calculate the pressure and other quantities, just using considering the gas of hadrons and then zero gas. As you increase the temperature, of course, it means that you create more and more hadrons, or when you increase the density, as the temperature density, you create more and more hadrons. Volumes at some point, they start to kind of get closer, bump to each other. In that case, of course, the energy is not so small anymore. They start to overlap, and in principle, in the transition, this gas of weakly interacting hadrons is no longer valid. So you also view it geometrically that once we have a kind of dilute gas, a weakly interacting gas, the quarks are kind of clearly confined inside the hadrons, but once you start heating up the system and these hadrons start to bump into each other, of course, it's kind of the question to which hadrons in the given quark belong, or which hadrons is confined is kind of less so clear, so it's more blurry. And if you keep increasing the temperature, you have kind of more and more overlap between these hadrons. So then, of course, in the extreme case where you at very high temperature, very high densities, and then you have a complete overlap of these hadronic states, the hadronic bags. You have kind of one big bag, and that in that case, the question of hadrons belonging or the quarks belonging to a particular hadron no longer makes sense. Now, of course, in this regime, you could think that, well, the energy is very high, so the distances between quarks are very small. That means that the coupling constant is becoming weak because of asymptotic freedom, and therefore you have a gas, so to say, a gas of quarks and gluons. So that's what the state of matter, what we call the quark-gluon plasma. Of course, at very high density, you have a degenerate quark matter. It also similar logic applies as the interaction between quarks becomes weak. So that's relevant for the compact stars. This high temperature matter is more relevant for physics of relativity. Sure.
At high density, what is the argument that alpha is small?
Because you have a Fermi momentum, right? So the Fermi gas. So Fermi momentum is large if the density is large, and that gives you the typical state. That's the same argument. So typically we think about the QCD diagram in the plane of temperature and the chemical potential, and I apologize, of course, it's supposed to be animation. So when you look at this phase diagram, what we know, and I will show in a moment, a small density and high temperature, of course, the transition from this hadron gas to with a broken chiral symmetry to the quark gas is kind of a crossover transition, or quark-gluon plasma, right? It's a crossover transition. As you increase the density, there will be an endpoint, and then the transition turns to first order transition. So here you have a hadron gas with chiral symmetry broken. In the high temperature, high density phase, you have a quark gas, quark-gluon plasma with chiral symmetry resolved, chiral restored, and also because it's a plasma, you have also color spin. Of course, we can't explore in lattice QCD all the phase diagram for the reason I will explain in a moment. So we typically have this segment of high temperature and moderately high density, or very small density, depending. So this is segment we could calculate things on using lattice QCD, and that's where we explore. So we could go actually to very high density if we also go to high temperature, but we cannot kind of go to the generic limit. The density, the resonant temperature is small, and the density is very large. So that doesn't work. So now, if you compare this matter to kind of ordinary matter, you really think, or you could really see that it's kind of it's a matter extreme. So here is all kind of interesting system. So it's a function of density and temperature. So on one hand, you have the ultra cold atoms, very low temperature, very low density. They are also strongly coupled in some sense. You could use that there's a surface of sun, it's hot, it's not very dense. And finally, you have sun, which is much hotter, or even supernova, which is somewhere it's here. But by all account, I mean, quark-gluon plasma is depending, of course, what kind of parameter you dial in, but certainly is the most is the hottest type of matter we know, and depending on where the chemical potential also is densest, so it certainly could be as dense as cold neutron stars, but it's of course much hotter and much hotter than supernova. So of course, experimentally, one studies this state of matter in collider, particle colliders, and heavy ion collider, relativistic heavy ion collider in Brookhaven National Laboratory, and also at Large Hadron Collider in CERN. So where we collide heavy ions, so either gold on gold or lead on lead, so somewhat larger energy. And the interesting outcome of this experiment was that the created matter in this collision behaved like an almost perfect fluid, so it has very low viscosity, it has very high degree of conductivity, and that means that kind of quarks in this matter still interact strongly. So contrary to this very naive expectation that, which is certainly true in asymptotic limit, and you go to very high temperature, but kind of a temperature which you could achieve in this collider experiment, quark-gluon plasma is strongly coupled. And of course, the question also for lattice QCD calculation, how this strongly coupled plasma arises from first principle. So how do we see that it's really, you have such a state of matter that is consists of quarks and gluons, but nonetheless is strongly coupled. So the way we do the calculation is basically we do a simulation of QCD partition function, and the idea is here that if you want to evaluate some observable O in a thermal ensemble, so you have to evaluate the trace of this operator with your statistical operator given by beta H, so that's the thermal part, and if you have conserved charge, let's say net value densities, and of course there is a chemical potential associated with it. And you treat this statistical operator as a evolution operator in imaginary time, so pretty much standard activity in quantum mechanics. And you rewrite this evolution operator in terms of a functional integral over the gluon field and the permanent fields. And now the effect of your temperature density encoded in the boundary condition. So the gluon fields are periodic, because they're bosons in this imaginary time. So the beta is the inverse temperature that's extended at the imaginary time, and the quark fields and permanent fields are antiperiodic. Now the problem is that, well, first of all, the one problem, obvious problem is that quarks are the Riemann variables, so you can't use put that on the numerical course. You have to integrate the Fermi results, which is easy because the Fermi action is quadratic, so that gives rise to the Fermi determinant, and just do integration with QCD action of the fermions. It's a basic Gaussian integration with Riemann variable that gives the Fermi determinant, and you rest with the gauge field, and you discretize everything on the space-time direction, which of course has a topology of torus because of this periodic boundary condition. So that's kind of our kind of lattice with periodic boundary condition. And of course, now we could actually calculate this integral, because now it's no longer a functional integral between a finite box in a discrete space-time. It becomes an integral of very large dimension, 4 million, but it's finite dimension. So you could certainly do this integral. Of course, there's some additional tricks like the gauge fields here. We compactify by putting it kind of writing in this form, so they become part of SU3 group instead of SU3 algebra. Now it's all fine. You could now evaluate this dimension, very large dimension of these Monte Carlo methods. In principle, that's of course as long as mu equal to 0. So of course, then you could evaluate it using Monte Carlo method because the determinant is real. So you could interpret this part of your integral as a weight. So you do Monte Carlo sampling. The problem is that when mu, the chemical potential non-zero, this determinant is non-complex, and then of course the standard Monte Carlo method fail. So that's known as a sign problem. It's not just for QCD. It's kind of large class of physics problems suffer in this value. You cannot do important samples. It's difficult to calculate. So that if this, okay, so Z3 it worked. If you do SU2, then it's special because SU2 is real, and then of course you could still simulate it. Real chemical potential, and that's particular feature of SU2 because the fundamental derivative is quasi real. So SU2 is the only gauge group where you don't have a sign problem. But in all other cases, that we cannot directly simulate. So what we could do instead, we could, at least if the chemical potential is not very large, you could use Taylor expansion and calculate different quantities as a Taylor series in the chemical potential. Now, of course, on the lattice, you have to take the continuum limit, so that means that the lattice spacing A should go to 0. Now that means that of course your temporal extent has to be very large because temperature is fixed, right? So one of the temperatures is given the number of time flares of the lattice spacing. So that means that n tau should go to infinity such that n sigma of n tau should be fixed. That means that you have also very large boxes. That of course means that if you want to take the continuum limits, the cost will increase. So the typical increase as an inverse 7th power of the lattice space and the number of temporal extent to the power 7. So meaning that taking the continuum limits, of course, comes at a penalty. So that means that in practical simulations, the larger than tau, kind of the better is the calculation in the sense that you are closer to the continuum limit. And of course, also the difficulty is going to small quark masses because the costs go like inverse of the quark mass and going to like quark mass is also.
Why is that 7 power?
Okay, so that's okay. So let's see. So you have 4 power is easy to understand that just for the now then you have an additional power from the quark mass because now the quark mass is also in lattice unit. So smaller quark mass means small lattice spacing means to get the same physical quark mass. You need a small number, so the n in lattice unit also, so that gives you 5. And then there are 2 powers from basically from autocorrelation, so then you have a system to small lattice spacing, the autocorrelation on the carrier. Of course, so the 5 power is 7 or 6, as of course debatable. Usually depending on how the
also depend on just for the base configuration. The correlation, autocorrelation problem.
Yeah, that of course it also observable. So that's just what I'm asking. So the autocorrelation, of course, is like 6, 5, or 7. So 7 is kind of maybe the most 5. Such a quantity, but yeah, in the worst case scenario, 7. Okay, so that means that, of course, if we want to kind of improve the fidelity of our calculation, we have to need a larger and larger computational power. So we use supercomputers to solve it. And what is a supercomputer? For those who are not familiar, that's basically taking your laptop and multiply by million. So it's like a million of laptops bundled together and kind of course, in physical is the way it looks like. It's showing this picture, so that's kind of one of the fastest computers in the frontier. So we have some allocation also around calibration there. So that's of course a powerful and a very energy consuming beast. It's not easy to get onto it, right? So that also needs very high performance code to demonstrate it in the efficient discussion. Okay, so now let me come to some results. So I talked about the chiral condensate psi bar psi, and what you want to understand is how this chiral symmetry gets restored. So I mentioned that it's a vacuum, psi bar psi is non-zero. But if you go to high temperature, you expect this condensate to drop to 0 because, of course, if you have a liquid in the vacuum core gas, there is no chiral condensate in that case. So what we expect is this chiral condensate will eventually decrease as you increase the temperatures. And of course, for practical reasons, of course, you have to realize that this object needs renormalization. So you have to construct a kind of quantity which takes care of the renormalization, but that's kind of a technical aspect. So we use this combination of the chiral condensate. It has kind of the chiral condensate, the limit of massless quark at 0 temperature, the chiral condensate at 0 temperature, and finally the final temperature. But it's a good proxy of what you would want to see. So here I show this renormalized chiral condensate as function of the temperature. And you indeed see this drop of the chiral condensate at around temperature 156 centigrade. So it goes to the vacuum value at very low temperature, and then as you increase the temperature, it kind of rapidly decreases, and then kind of slowly decreasing and goes something close to zero. So indeed, the chiral symmetry gets restored because it's.
For the blue points, it seems to be difficult.
Yeah, and that has to do with the fact that when you do the subtraction, right? So strictly speaking, you could only have a well-defined chiral condensate in the chiral limit, because then by just multiplying by the strange spot mass, you have a renormalization with invariant quantity. There is no kind of power divergence. Now, if you had the quark mass, here I subtracted the vacuum part from the finite temperature part to remove the power divergence. And kind of because I subtracted it, I added back kind of in this D term, which is a chiral condensate in the vacuum, but at the little more time.
The critical temperature is.
It's just that doesn't matter, right? I mean, in fact, you could. So here I took the renormalized one because otherwise, I mean, the horizontal, the vertical axis didn't make sense. Of course, I don't have to do it. I, for example, just can take the bare condensate, right? And if I look at the fluctuation of the condensate, and then the fluctuation of other parameter chiral, so that's fine. So here I show the disconnected chiral constant susceptibility, which is a fluctuation of psi by psi. And I know that the fluctuation of the order parameter has a peak as a crossover phase transition temperature, and here's the same, right? So the fluctuation of psi by psi has a peak. And now the question is, how do we know it's a crossover? It's a, let's say, second order phase transition or first order phase transition. This peak, when I increase the volume, will go to infinity, right? Because you tune the system to criticality, and infinite volume is the fluctuation infinite. Yes.
Exactly at the critical temperature or near to it, what is the typical correlation with one? Why I'm asking is that let's have a QCD we see in heavy ion collision compared to that scale of the QCD in heavy ion collision. What is the correlation?
Yeah, okay. I mean, here we, of course, on the lattice, we try to take into account, right? And what I'm showing here is two volumes, different by factor 8, and you see no change in the height of the stability, which means in QCD,
yes,
this
correlation length is finite, not scaling with correlation.
Right.
But what is it? Is it in per minute or what are the more?
I think it's of orders of power mass. Doesn't decrease, right? I mean, in principle, you could imagine that for sigma mass, if you would go to the higher limit, if you imagine a sigma field going to 0, the mass of sigma field going to 0. But if you say that the physical form mass basically 1 square, so it's relatively small kind of thing. Yeah, so
The critical modes are the same. Actually,
the critical modes are the same, but basically what this problem is the fluctuation is sigma c, right?
the inverse of mass of that will be the correlation.
Yeah, the problem is of course calculating this difficult, right? Because you need to disconnect the power.
What is the lowest mass it will see for the sigma measure? Is function of temperature.
Well, it's a sigma mass on, it's 400 MeV, right? And it doesn't change much
Near to the
near to. Now, as far as we could tell, we never really calculated it because it's a hard calculation. There is no indication that it would go to.
so that will save the correlation.
Yeah, that's what.
Very near TC, but below TC again the pions will set the correlation.
Below this is a bias, and the sigma is silent. Yeah, so basically from the fact that the chiral susceptibility doesn't show finite size effects, we know that transition is crossover. And by the way, this calculation, this was experts was done this domain of the Okay, good. So now, what else can we calculate? We could calculate the equation of state, and here I show 3 times the pressure, the energy density, and 3/4 of the entropy density, scaled by appropriate power of the temperature, and then everything here is scaled either by T to the 4th and T cubed, and just curious thing to see that, right? In the textbooks, we know kind of physics class, pressure is proportional to temperature. But here I normalize the pressure by T to the 4th, and so why is that? It's just because the pressure is certainly true that it's proportional to the temperature, right? But it's proportional to temperature times the density. As the density in ultra-relativistic system is also increasing with the temperature, so the density itself goes up. And therefore, in contrary to non-relativistic systems, the pressure in ultra-relativistic system, I think, was not very high temperature scale T to the 4th. So here I show 3 times the pressure, the energy density as function of the temperature. And so first of all, what one sees that up to the crossover temperature, the pressure and energy density are shown from the lattice calculation as these bands. It follows the prediction of the hadron resonance gas model. So that's just illustrates again that at low temperature, the system is indeed behaves like gas and hadrons. Of course, not completely just hadrons, because hadrons have interactions, and some of this interaction can be incorporated by including hadron resonances. So resonances, or the interaction between hadrons kind of mediated by resonances. So we take the non-interacting gas of hadrons and resonances, but once you take also hadron resonances, then you get a pretty good description of the pressure and entropy density, energy density. And then if you go to very high temperature, of course, you could use a Stefan-Boltzmann law to predict what the pressure should be, just counting the degree of freedom and multiplying by T to the 4th times the appropriate constant, pi squared or whatever is in there, right? And this non-interacting limit I show here as this dashed line, and you see that it's 400 MeV temperature, you're maybe like 15% below. So indeed, the system goes from a hadron gas, which is kind of weakly interacting, to another weakly interacting system, quark plasma. But in between, of course, it's kind of neither, right? So here, of course, you can see what we expect is that it's neither hadron gas or quark plasma. It's really strongly interacting. It's also that you could look at speed of sound. So speed of sound spread in a massless ultra-relativistic gas is 1/3. So again, the speed of sound in QCD goes to 1/3 at very high temperature. At low temperature, you could also calculate the hadron resonance gas. Lattice calculation agrees with hadron resonance gas pretty well. And the energy density actually at the transition temperature of the pi is about 400 MeV, which is kind of the energy density in the inside of the proton, and it's 3 times larger so than the energy density of normal nuclei.
The energy density and pressure at very high temperature to become a constant.
Yes. Of course, you don't see it, but if you would calculate at high temperature, which we did, then it's roughly constant.
And it deviates at low temperature because there is some mass.
Yes, because it's low temperature, it's not quarks and gluons, right? It's massive hadrons, right? And therefore you don't have this kind of Stefan-Boltzmann-like behavior. You have some increases because right, so this as the temperature becomes larger and this Boltzmann suppression of heavy hadrons, protein, etc., becomes less effective. And of course, on the other hand, you also produce more, right? So it also produces effect.
And so the degrees of freedom are different, right?
Very different.
Colored object from left side.
Yes. And of course, the question is, what the interesting question is, which I will try to answer in a moment, what happens in between? And that's not. So you see that the pressure itself is kind of halfway between the hadron gas, which is somewhere here, right? And the quark gas. What the matter is, that's a good question.
There's a departure from conformality. Stay still like 1 GeV.
Yeah, that they didn't show. Of course, if you would calculate epsilon minus 3p, which is a trace anomaly, of course, you see that the pressure and energy density very different, right? In conformal system, or also was high temperature, of course, they go together. Here's the difference is pretty large, and if you would actually quasi-trace normally, so trace of energy boundary, that would be better. I didn't show it because.
And it stays still 10 GeV.
Well, of course, because it's strictly speaking, is a conformal normally never zero, right? Because of coupling bonds.
Yeah.
And so yes, but at high temperature, it's basically just running with the coupling bonds. So of course, it's not completely constant, right? Also here, the pressure won't be completely constant because the coupling chain there will be slight variation. So there's
So yeah, the thermodynamic system, how does it know about the coupling and its dependence?
Because it's a quantum field theory, right? So typically when you think of quantum system, you have alpha electromagnetic, which is 137. Of course, we know alpha electromagnetic is not 137 if you explore quantum electromagnetism by the wide varieties in back in that experiment. It's 138. So 137 is actually the coupling constant. Like high energy increases. Oh, sorry, it's one of the slides. One of the alpha is not 137. So the QED coupling constant become larger. High energy, that's never a constant, but that's a fact is very high in QCD because you started with a relatively large coupling constant.
Yeah, see the
It's running.
Yeah, in terms of thermodynamic quantum somehow it knows that.
It knows that, right? Because it's all the quantum fluctuations are built into the system.
It's just a bubble that.
Yeah. So yeah. So to calculate the pressure and the gravity, it knows about that. As a trace anomaly is done. Okay, so all right, so let me go back. Okay, so now I mentioned that we cannot calculate the pressure at non-zero chemical potential because of the sign problem, but what we could do, we could write the pressure as Taylor series in terms of the chemical potential. So of course, if you have three flavor of flux, up and down is strange, then there will be this three chemical potential, or you could also write down in terms of other set of chemical potential, which is with barrier number, electric charge of hadron and strangeness, and of course these two ways of writing the pressure is equivalent, so you could kind of trade these three chemical potential, barrier number, electric charge and strangeness, with respect to quark chemical potential QED and S quarks. And this Taylor expansion coefficient, of course, you could get from the Euler's partition function relatively zero chemical potential. So in principle, this coefficient can be calculated by Monte Carlo method because you evaluate zero chemical potential. And this Taylor expansion coefficient, also called susceptibility or general susceptibility of conserved charges, are interesting because they characterize the correlations between conserved charge x and y, or fluctuation of some conserved charge x, which could be a barrier number of electric charge. And therefore, this quantity in principle carry information about the carriers of conserved charges, whether they're hadrons or quarks, and in this way they also can be defined.
So, I know you do not expect large chemical potential.
Yes, at high energy colliders we don't expect. Go to lower energy, for example, realistic hadron collider is very exact, and go to lower energy, you'll see that the chemical potential will increase basically from nearly 0 at 20 and maybe to something like 200, 300. Or even bigger. But at the top energy, of course, the chemical potential don't.
There is an experiment called Nika, right? Russia,
Yeah, I mean, it's not here than they never will.
Yeah.
Yeah, but in fact, in the week,
GSI is coming.
GSI is coming, but in fact, if you do low energy collision, so if you go below the injection energy, which can be done, so you kind of inject and accelerate the beam, so you go to from 200 MeV, 200 GeV to 7 GeV collision energy, pretty much simulate the maximum barrier density that can be created by the collision. So in principle, Rico collisions it's very low energies that GSI will be doing. Of course, with limitations that of course it's a collider, it's a different detector, so luminosity is an issue, but a lot of physics brings it to is can be explored and data collected. Just
But there is a critical density. Beyond that, it's not possible in heavy ion.
yes, because certainly it's not a freeze out. So the freeze out the density kind of increases as you go to lower beam energy, and if you decrease the beam energy further, it actually goes down. So there is a maximum energy around 7 GeV.
But they're
Oh,
just
maybe
fixed
they-
target. Fixed target is not good.
No, you're saying for fixed target. It's the fixed target has the advantage that that you have you could sample much bigger windows. And of course, you could also operate in fixed target mode. The problem is that if you operate a collider detector in a fixed target, then it's not optimized for that. So there is better way to do this low energy experiments done. And
Radius is also going to very low energy. Radius.
which exam?
Radius.
This year, because that's even that's much as great basic physics. It's not, I mean, yeah, so it's very. Yeah, okay, so now, so have a look how actually it behaves. So again, on the lattice, we could calculate the fluctuation of barrier number, electric charge, and strangeness as functions of temperature. And here I just normalize everything by the corresponding ideal gas Boltzmann values. So therefore, at high temperature, you get close to 1. If you kind of take into account the ideal gas limit of the mass of quarks, right? You could calculate these numbers, and what you indeed see is that when you look at the barrier number, electric charge, and strangeness at high temperatures, they really described by the quark gas limit. At low temperature, of course, I showed these lines, and these lines corresponds to the hadron resonance gas calculation. So, in other words, these fluctuations at low temperature are described by hadron gas, that is, the conserved charges are carried by massive hadrons. At high temperature, they're carried by kind of essential massless quarks. So that's what we learned from this calculation. You could also look at higher order fluctuations. So that's the second order fluctuation. You could look at fourth order fluctuations and kurtosis of barrier number. And in particular, you could look at this. So basically, kurtosis is the ratio, the force, the second order fluctuations. And that's interesting in the sense that at low temperature, it goes to 1. And that's what you expect. So at very low temperature, you have only baryons, as the only degrees of freedom, or anti-baryons. So we have the only carriers of barrier numbers either B equal 1 or B minus 1 objects of baryons, anti-baryons. And therefore, you have second order fluctuations being 1, fourth order fluctuation being 1. So the ratio is also 1, so everything is 1. Now, if you go to on the other extremes, right, the very high temperature, we have now 1/3 and minus 1/3. And the second order fluctuation will give you naively 1/9, right? And the fourth order fluctuation 1/81. Basically b to the 4, so just 1/9 squared. And when you so then there's this ratio of the fourth order to fluctuations is again will be 1/9. So the statement is that if you go from a hadron gas to a quark gas, this ratio of this ratio of fluctuation of the kurtosis should drop from 1 to 1/9, and what you actually see that is indeed happening around the crossover transition. You see this switch from 1 to at some high temperature 1/9. So here you have a quark gas, here you have a hadron gas, and of course the interesting question: what happens again in between? So right between those two limits, slightly above the transition temperatures, neither the quark gas nor the hadron gas.
So you can see that 1/3 also directly.
Yeah, so that's the idea, is that you see the 1/3 directly because you don't see 1/3 directly because the reason is that you don't have net quark density, right? Because your chemical potential is 0, but the fluctuation of quark numbers is that quark number is 50, but the fluctuation of quark numbers is 1/9. And if you look at the higher order fluctuation, the fourth order fluctuation, 1 over 81. And the ratio is 1 would be nice, yeah. No, the problem is the experiment that of course you go to. Actually, the idea is yes, but not this one. What you observe experiment is fluctuations somewhere here, right? Because the idea is that when you reach the transition temperature, the system falls apart. So if you have fluctuations around the transition temperature, that of course you could measure principle because that's when the system was still in equilibrium. To measure fluctuation at the last stage when the system was in equilibrium. And then it's decoupled, nothing happens, but you lose the information what happened at very high temperature, right? Because if it's a thermal system, it forgets where it came from. As it cooled down at transition temperature, it was still a thermal equilibrium. So here, of course, you could measure the fluctuations at the TC, and then it falls apart. And when you do this comparison, it seems like what you calculate here on the left is what you think you're measuring, of course, the addition how well, it's not easy to measure it, but if you believe that the experimental did a good job in kind of correcting for kind of the technical acceptance of the volumes, then what you say is correct, but it can be observed at TC. So okay, so I already mentioned that here we have a core gas, right? But we always see some deviation from that core gas in principle. And now the question is, can we understand this deviation, right? So it was never really ideal core gas, but close. So this now we are looking at asking the question, can we understand this deviation from core gas quantitatively? So again, I look at the second and fourth order fluctuations of U quark number divided by the ideal gas value. So ideal gas is 1, the lattice data below 1. And now, of course, you do perturbation theory around the ideal gas value. So you calculate this object high temperature using perturbation theory. You need some version of perturbation theory. It's called the main HDR with some electrostatic QCD. So there's some version of the perturbative series. And once you do this resummation, actually, it turns out that this uncertainty, which is kind of this band, or this dash band, of course, the lattice data agrees with a decoupling calculation. So it's not only that the lattice data is close to the ideal gas, actually the deviation from the ideal gas that's seen on the lattice also can be quantitatively understood to do perturbations at high temperature. Now we also could scrutinize a little bit the agreement with the hadron resonance gas. So here I show second order fluctuation for baryon number, strangeness, and the cross correlation between strangeness and baryon chemical properties and baryon charge. Okay, I have to speed up because it's already 1 hour, but let's spend some time on kind of setting up. So sorry about the delay. And here we could do the continuous extrapolation. So this shown is this band. And again, we can compare with the hadron resonance gas, but the hadron resonance gas doesn't always work that well when you have a closed loop, for example, here, right? So the hadron resonance gas is black line. It includes all the known hadrons and the hadron resonances in particle data group. And that's not enough to explain the data qualitatively. And that's because the hadronic states, which are not yet observed, but predicted to exist by lattice with a head and quark model. So when you include this additional states, and then only then you get a good agreement with hadron, between hadron gas and this fluctuation of baryon number, strangeness, and this cross correlation between baryon numbers, the strangeness. You could also do this comparison on high order fluctuation. And here, even if you include all the states, the agreement is not so good. So we see agreement below 140. So then if you go 145, 150, the agreement is not so great. And it's actually, if you go to higher order fluctuation, the 6th order fluctuation, 8th order fluctuation, it becomes, in fact, worse. So you don't see agreement. between hadron gas and lattice calculation of higher order fluctuation, but that can be in fact understood because the hadron gas you only take only into account the attractive interactions. So all the interactions between hadrons are essentially attractive, so they're mediated by resonances. But there, of course, could be repulsive interaction between hadrons which you don't take into account. And it turns out, and of course, you could show it that somehow when you go to higher order fluctuation, the practically small repulsive interaction that it has. So you could try to include them and try to include this Sayatan in the mean field model. And when you try to include them, so here I show the lattice results, the continuous separative lattice result is this gray band. And in this model, there is a strength of this repulsive interaction, which has this parameter K. And you tune it properly such to reduce the second order fluctuations, and you get slightly better, right? So you improve tuning parameter to improve the agreement having gas and lattice slightly better. Then you get very good agreement for the fourth order fluctuation up to the transition temperature. And you could also calculate even the sixth and eighth order Taylor expansion coefficient pretty well.
Sorry, this is a repulsive interaction between the hadron.
Right. In that case, between variants.
So what is the order?
If you take a nucleon and a nucleon, also sorry, nucleon and bring them so distantly, then they repel each other. And so if you, no, it's not Coulomb, it's strong. Right, so it's proton and neutron, two neutron. So just think of neutron, right? I mean, Coulomb repulsion also is kind of its strength is order of magnitude smaller than a strong interaction. So there's if you think of nuclear forces, right, I mean, the positive kind of attractive at or negative in a sense, right? So the potential negative and attractive at intermediate distance of order 1/3, but if you go below 1/3, then it's repulsive. Right, and this repulsive core, right, which is you can potentially repulsive core is the origin of this. And so that's what we try to include in kind of schematic scheme. So it's around different way to do it, but essentially you say that there is if you increase the density, then there is you increase the energy because then you put more nucleons in a box, right? And then essentially this parameter K is dependent on this value of the policy. It's very similar.
It's effective also in the turnover of the.
Oh, that's of course we don't do it. I mean, you can. I mean, of course, if you construct a wonderful startation state and then people who do kind of nuclear material high temperature do it, but for us, we at high temperature, so we don't care about this interaction.
No, that is, you can see that.
Well, in the sense that yeah, you could, but that's a different calculation. It's not this. Then you have to calculate the nuclear potential people are trying to do. Yes. Yes. So there's calculation. So yeah, you see the response core. Yeah, it's non-terminologically, but now you can see the lines. But that's not what we're doing here. We just have this one parameter which multiplies the density and that goes to the energy of your gas, and then the density increases as this interaction. And then that, of course, captures all of these results. Okay, so now we could also look for charm degrees of freedom. So we could calculate this general isosceles also for charm. And again, you could look at the ratio of different charm baryon correlations, which in hadron gas should be all 1. And in the quark gas, they could be very different from 1. And again, so that is calculation shows this transition from 1, right? That's because basically all the charm baryons responsible, all the charm baryons responsible for this baryon charm correlation, whereas at high temperature you have the charm quark, which carry 1/3 of baryon and 1 unit of charm responsible. So that's why this ratio kind of goes to 1/3. you could also look at the baryon charm fluctuation divided by the charm fluctuation itself, the force order, and that's kind of a proxy, the charm baryon pressure to the total pressure. And again, you could compare this hadron resonance gas. And again, if you just include the known hadrons from particle data group, that's not enough. But if you also put the charm hadrons, charm baryons, which are predicted by quark models, and you get a very good description of this quantity, or this ratio of baryon charm correlation to charm fluctuations.
So sorry, you attribute that to the charm because of the place where it turns off. The mass of the charm core.
Yeah, I mean, it's always small, but that of course taken care of because I look at the ratio. So imagine you have a system where you have, in addition to up-down range, you have charm. Of course, the charm quarks, because of Boltzmann suppression, are much smaller, but that's irrelevant. You just now look at the kind of the fluctuation of different charm correlation from baryon and their charm correlates. Of course, those are absolute number very small quantities, but because they're non-zero, you could calculate them.
So I guess I'm asking, how do you know that it's charm and not a stain or an alpha?
Oh, because the charm has a separate chemical potential, right? You can't explain the charm in a strong interaction, right? The charm is a fixed number.
But in a simulation, I'm saying like for this data.
It's the same thing, right? So you put the charm chemical potential, you have another kind of conserved charge, and you start the fluctuation. Okay, so now what we want to understand, go back, right, is again this intermediate region where it's neither hadron gas where it should be 1 or quark gas where it should be 3. So what's going on there? So we came up with a model with Sayatan several years ago where we kind of said, well, of course, at low temperature, you have charm baryons, you have charm mesons, but of course, if you go above the transition temperature, the charm quark degrees should appear. So we have some deconfinement transition or kind of quark liberation at about PC, about the crossover temperature. So let's add the charm degrees of freedom. So we write charm pressure of charm degrees of freedom in this form where you have charm meson, charm baryons, and charm quark. And if you have these fluctuations, right, you could calculate from this form of the pressure, which only relies on Boltzmann approximation, these different quantities like charm fluctuation, baryon charm correlations of different sorts, right? So if you have 3 input quantities, in principle, you could extract this partial pressure of charm quarks, charm baryon, and charm mesons. And that's what we did. So we calculated this quantity of the lattice. This, of course, unknown, but with these 3 lattice quantities, we could kind of calculate these 3 partial pressure. And here I show this partial pressure divided by the total charm partial pressure, so everything included. And you see that the total charm pressure at high temperature, which is these red points, is actually dominates the charm pressure. But this charm pressure, of course, goes to 0 around the transition temperature. And if I look at low temperature, it's dominated by mesons and has also some baryon contribution, which, of course, at high temperatures, they go to vanish because eventually baryons and mesons, they will melt at high temperatures. So we have this transition from 4 degrees of freedom, so 4 degrees of freedom appearing, so the corresponding contribution to the charm pressure increases, and the meson and baryon contribution slowly decreases. And of course, that's kind of what we found then. The problem was that the errors were pretty large back then, so we couldn't see very clearly. But now we had recently a much more improved calculation with another Sharma, who's now in view at the postdoc in view at Sipa Sharma. The same idea, but now with much more statistics, and we see clearly that the quark pressure is 0 up to the transition temperature, and then just above the transition, it goes from basically 0 value to some non-zero value. The meson charm pressure, which is very well described now by the hadron gas shown in this line. Suddenly deviates from hadron resonance gas and start to decrease, and the same for baryon. So the baryon pressure up to the transition temperature is agree with hadron resonance gas and then start to decrease again. So what we see is that chunk wall degrees appearing just above the transition temperature. Mesons and baryons are slowly disappearing above the transition temperature, but they're not kind of immediately, so there is no step function. Yes, please.
You got all the partial pressures for all these forms. Now, how do they compare with the partial pressures?
Oh, that's a more difficult because once there is no.
But you know the total pressure.
Yeah, so if you wish, you could if you have a proxy of this partial pressure, that can total to the rest of the total.
How does that happen?
I never looked at that, but
it sort of tells you whether it's dominated by these block pressures or by the pressure.
well, I think the core pressure will be dominant in a sense that it's like 2/3 to 1/3. So the core is maybe 1/3. Also, yes, it's basically 1/3.
At the crossover.
Yeah. Or
Yeah, I can see that.
higher.
At the crossover.
Tornado is blue ball. Blue ball is around 1800 ml. It's much more subtle.
Yeah.
It sounds something dominant.
Right, it's a bit more tricky because I mean if you look at the proton, right, it still has a lot of groups. So how do you identify it, right? And there is no easy way. So here, so yeah, you could do a rough estimate, but it's not a very precise estimate in the sense you can't quantify even the light pole pressure. So the reason I could quantify the charm pole pressure because I need support on approximation. The charm are heavy. And then, of course, I can quantify it. But the core pressure itself, I cannot do. I cannot quantify it without additional model dependence. There is a model dependence.
All the core pressures are doing essentially doing the Taylor expansion.
No, I'm calculating population of core number. There's not a core pressure. So the population of the core number.
The chemical potential has been secret in that thing.
Yeah, but it doesn't give you core pressure. It gives you
all the effects of the curve, the density of the core pressure fluctuation, all that is coming from only the chemical potential. You are treating that in that expansion. So anything else would be much more complicated. But since you have done this already in the Taylor, what is the rest? That would be a useful number to know.
Yeah, but what I'm saying is that this quantity that's the root of that. So you see, when I write the charm pressure, right? If I know the charm pressure, I know that charm susceptibility was right because the chemical potential dependence is and the temperature dependence factor rises here. But in general, it's not true, right? So you have a function, the pressure is a complicated function of the chemical potential, the temperature.
That is, but when you are simulation, the way you put in the chemical, you're not putting the exact, you're using Taylor expansion.
Yes.
It is for that reason I'm saying. So you are doing it in that sense, although this is a parameterization of your answer. But you are anyway doing it.
Yes.
And therefore, anything else apart from that, you have to attribute it to the rest of the interactivities, which includes a glue on that.
Yes.
So, what is the magnitude of that compared to magnitude of these that you have? I mean, some idea how much.
Yeah, I'm saying that there is no model independent way to separate.
That's good.
Model dependent way, of course, you can do it. But that basically what you have to do, you have to treat all the quantities, the pressure, the total pressure, the susceptibility with some quasi-particle gas, and that quasi-particle gas partition down. Here, of course, I didn't talk about any quasi-particle station, I use a Boltzmann approximation, but that's just the statement that the charm clock mass is much bigger than yeah, and there is no model of it, right? You're just taking the known fact that the charm is heavy. And then, of course, you could extract the pressure model in the kind of way, but the light plot is not bigger. That's a complication. Okay, so now with Taylor expansion, we could also calculate the pressure at large density. So here I show the baryonic pressure, so the pressure with respect to u equals 0, so delta P, the change in pressure, when I include the chemical potential, so with respect to 0 chemical potential. And you see that as I increase the baryon chemical potential, this additional contribution to the pressure, the baryonic pressure increases. And here I show different order 4, 6, and 8s, and up to mu b equal 2, all this expansion gives you the same result. If I go to high temperature, of course, I could go even to much larger mu b in principle. So the statement is that with Taylor expansion, I could calculate the pressure up to mu b over t for 2.5. If I want to calculate QCD 180 MeV, I could in principle even go higher. We also look at the speed of sound at different baryon densities. So this kind of we parameterize the baryon density as the ratio of the entropy density baryon density, meaning that the smaller this ratio, the larger the baryon density, because entropy is always something, right? It's everything. And you see that, well, there is not much change actually in the speed of sound. So as you increase the density, there is no softening of the equational state, there is no decrease in speed of sound as you would expect if you would approach second order phase transition and first order phase transition. So the speed of sound is unchanged, or actually slightly increases with increasing
Never goes to beyond 1/3.
It's never close to 1/3, yeah.
So, do we understand why there is a minimum?
No, eventually this the speed of sound square should go 1/3 because it's a pure gas. In hadron gas, it actually also 1/3 if it's only time. But what happens in a hadron gas that as you increase the temperature, heavier and heavier particles start to contribute. And if you have heavier particle contributing to the thermodynamics, it will make the speed of sound smaller, right? Because you increase the energy density a lot, but you don't increase the pressure because heavy particles dominate the contribute to energy density much less. So the softening of the equational state means that as you increase the temperature, the importance of these heavy particles, like baryons, kaons, become important. Before that, it was only ion gas, but now it's kind of a mixture. And this additional heavy particles in the systems go down. But then you reach the transition point, and eventually you have to go to the pure gas. So the hadron gas goes down, eventually it has to go down. It doesn't have to be.
Does it have to be?
It's close numerically, but it's not that bad.
So that means there is some.
So this crossover. So the minimum doesn't not because they're close to phase transition. It's just an interplay between different hadron species in the hadron gas, and then of course the breakdown of hadron gas and kind of slow transition to pure gas. This is a crossover. It has nothing to do. It has to do more with hadron composition than with the fact that it's a close to phase transition. And then the fact that the pressure goes, the speed of sound actually becomes bigger as you increase the density, kind of collaborate. You approach a critical point with that critical point and softening, so it actually becomes speed of harder. Okay, good. I just wanted to talk a little bit about heavy core diffusion coefficient. I don't have much time. Just mention that, of course, on the lattice, we could calculate correlation function Euclidean time. Things like transport properties of the matter, including the shear viscosity, as a transport coefficient, heavy core diffusion, are encoded in the spectral function, which is kind of the Fourier transform of retarded propagator. So you could take whatever operator you wish, typically some power bilinear, and you could calculate the corresponding spectral function. In principle, on the lattice, what you calculate is a Euclidean correlation function, but it's related to the spectral function with this integral representation. So if you have some information about the Euclidean correlation function, you could reconstruct, try to reconstruct and estimate the spectral function, but it's difficult, obviously. So now one particular interesting point is when you take a vector measure, so kind of vector current correlation function, there's this gamma matrix, which is gamma mu, you have a vector current, and this is a conserved current, so the corresponding correlation function, spectral function, has, in addition to all kind of other structure, has this structure at very low frequency, which is related to transport phenomena, and they include the transport coefficient. In this case, it would include the diffusion of a quark flavor, or if you have a heavy quark current, it will be a heavy quark flavor. And if you try to describe this structure, the spectral function has this shape of a kind of a Lorentzian, and it is narrow peak around omega equals 0. And the reason it's narrow is that because if it's a heavy quark diffusion, you could think in terms of the Langevin dynamics. So you have a drag force acting on a heavy quark and the random kick to this heavy quark on the medium, which is kind of encoded in the autocorrelation functions of forces. And the force-force correlation is basically gives you the momentum transfer from the medium to this heavy quark. So this kappa is the momentum diffusion coefficient, and eta is a drag coefficient. So that's a drag force acting on heavy quark, and in equilibrium, this coefficient is of course related by the Brown-Einstein relation. So if you know, let's say, the drag, the momentum transfer coefficient, so the momentum diffusion coefficient, you can estimate the drag, and vice versa. And of course, the drag itself is kind of related to the mean free path. So eta, the drag coefficient, is kind of parameterized in terms of the spatial diffusion coefficient, which is nothing else but the mean free path of the heavy quark size of this ds is a spatial diffusion coefficient. And what we try to do on the lattice is actually to calculate it, and the idea to calculate is actually simple. We want to, instead of kind of really trying to reconstruct the whole current correlation function, we want to estimate the force-force correlation function kind of in Euclidean time. So the idea is that this force-force in QCD is just a color of lens force. So you could write it, the autocorrelation function is the force acting on the heavy quark as a chromoelectric correlator and chromomagnetic correlation function. And this correlation function, of course, you could write down, or you could calculate on the lattice using Euclidean time, and this also has a spectral representation like any other correlation function. And then the corresponding heavy quark diffusion coefficient is defined by the Kubo formula, so the omega equals 0 limit of the corresponding spectral function. So you could write down the heavy quark diffusion coefficient as the kappa E diffusion coefficient related to the spectral function of chromoelectric fields, and the kappa B of the chromoelectric field, and this B squared, which is kind of the mass plus effects. That's a kind of magnetic field, and B squared is just 3 over m. So for heavy quarks, actually is dominant. So we did this calculation. I won't go into detail recently, and what we found is shown in this figure. So what is shown here is a heavy quark momentum diffusion coefficient kappa in T cubed units, because that's natural units if you go to high temperature. So roughly, if you go to very high temperature, the kappa over T cubed should be constant. If you calculate it close to the transition temperature, it is actually very far from constant, has a significant temperature dependence, and is pretty large, so compared to what you expect from the weak kappa, which would be somewhere here. We've also estimated the spatial heavy quark diffusion coefficient, which is a mean free path. And the results are shown here, and we compared with different other estimates. So the lattice results are these red points. The blue is all the previous lattice calculation done in bench QCD. So, neglecting is effective dynamical blocks, and neglecting basically the right block gives you the freedom, and that it gives you a much bigger mean free pass for the heavy blocks. So in QCD, in 2+1 flavor, because in real QCDs and mean free pass, and the S is very small, and it's actually close to the conjecture bound given by ADS CFT, so which is the possible mean free pass that any block should have. So the statement is this lattice QCD calculation that we did, they indeed show that close to the transition temperature, the mean free pass of the heavy block is very small, close to the ones which one would expect from very strong temperature system. Okay, so time is way over time, so let me conclude. So using lattice QCD, we established very well the transition temperature and the equation state for quark-gluon plasma. We have seen or confirmed that hadron resonance can describe various remaining quantities at low temperature by comparing lattice and the hadron resonance gas calculation. I kind of try to convince you that deconfinement transition can be understood in terms of fluctuation and correlation of conserved charges. So you see clearly a breakdown of pure hadronic description of these conserved charges around the current chiral transition temperature. But what's interesting that when we consider charms, that this fluctuation of the charm indicates that while 4 degrees of freedom appearing above the transition temperature, the charm hadrons still exist at temperature like 180 MeV. And of course, this charm degrees of freedom kind of underscores that the medium is still strongly coupled. At very high temperature, we could in principle use perturbation theory to estimate some of these fluctuation of conserved charges, and of course it all works out. But still, for temperature below 300, the quark-gluon plasma is strongly coupled, and the strongly coupled nature of quark-gluon plasma is also kind of seen in the results we obtained from the. Thank you very much.